Hi everyone, this is my fourth video. In this video, I'm going to try to apply more science, because for me it always makes more sense when I know what's happening, and perhaps this will help. I tried to make it as uncomplicated as possible. If you have any questions, leave some comments. I will try to answer them. So basically what we're looking at, why is this virus so difficult or so deadly to some of us or some of the older population? Its mortality rate, the rate at which it kills people versus flu. So flu kills 0.1% of the population normally every year. The coronavirus is around a 3% mortality rate, which is a lot higher. And why is this the case? Why are we seeing this? So I'm going to try to bring it together, and hopefully this also explains why we're also worried about influenza as well, because influenza does a similar thing. Influenza is probably worse. I don't know if I should make that statement. I don't know if I'm that expert to really know that, but they're both bad. We can leave it at that. So here we go. This is a brief immunology viral lesson, the interaction of the human body defenses with viruses. So here we are. The top one here, this is an antibody. And not only antibodies are working in your body to prevent infections, but the antibodies themselves can bind to the viruses, so they have a very difficult time getting into your system where they need to be. You look at these antibodies at the top right here, you see a blue square, a red triangle, and a green half whatever zit. That's what it looks like. It recognizes, this antibody specifically will only recognize things that have this combination on them. So when we look at the coronavirus, the protrusions right here, how it helps enter your system, it has the blue square, the red triangle, and the green zit. So the antibodies will bind. They will recognize this. It's basically organic chemistry. It's a bunch of chemicals, biochemistry. So these are chemical compounds that bind to other chemical compounds because they match in the right positions to bind with them. So what ends up happening is you have the virus surrounded by a bunch of these different antibodies because all these antibodies recognize this virus. And this virus, its ultimate goal is to get into your human cells. In this case, it would be the cells of the lungs. And you can see he's happy and smiling because the antibodies are preventing it from binding. These little binding points right here need to bind to your cell. But it can't do that if these antibodies are blocking it. The virus has to get into your system to replicate, to just give birth to more of itself. Thousands and thousands of copies. It needs to get into the cell, specifically where the little smiley is, called the nucleus. Well, not all viruses need to do that. It just needs to get into your cell. It needs to get into your cell to hijack your own equipment to keep your cell healthy and to repair damage and just to grow and make more cells. This virus will take it over. If your antibodies stop it from getting in, think of it as somebody carrying a bunch of shopping bags. A whole bunch of shopping bags grandma's bringing in, and she wants to get in the door, and she can't reach the door. She can't turn the knob because she has too many bags in her hand. Generally, we would set the bags down, open it up, pick the bags back up, go in. But these chemicals bind very tightly, these antibodies, so the virus can't get in. It's not going to get any help. It's not going to be able to shake off these antibodies. The antibodies fully recognize this virus to stop it from getting into your system. And like I said, that's not the only process happening, but for our sake of argument here, we know that actually antibodies can prevent or help you against coronavirus. Actually, they've been talking about giving antibodies that from people that have survived. It's passive immunity, it's called. It's something that babies have with their mom when they drink the breast milk. At any rate, these antibodies can prevent the virus from replicating, which prevents you from getting really sick. So in the case of what happens when the antibody is still the green zit, the red triangle, the blue square. I should have come up with something better for green, but anyway. So if the virus itself is a blue square, a black moon, and a green zit, so this antibody can still recognize this virus, but not as well as it would have bound. It's not the exact chemical signature it likes to bind to very strongly, but it can still bind. It can still prevent some of the virus from getting in. There'll still be some reaction, and these antibodies activate other things to prevent the virus from replicating. But in this case, they don't bind as well. They might bind. So when you hear a vaccine's maybe 30% effective, this is what a lot of people miss. 30% effective means that, it doesn't prevent the illness. It doesn't stop everything. But again, immunology is a gray zone. It's not black and white. If you get a vaccine and it has, some effectiveness to some parts of the I want to say antigen, but I know that's a big word in immunology here. It binds to the specific chemical signatures that the body recognizes. If it's a little bit different, it could recognize some of it, and it could mitigate some of the replication, and it can actually give you enough time for your body to produce a response that's better. So it actually matters if you have some immunity to a virus. But like I said, in this case, this would be some immunity. It doesn't recognize the black moon, but it recognizes the green zit in the yellow or the blue square. In this case, some of the virus gets into the healthy cell, and this is the DNA getting in, and it'll replicate somewhat. But again, having some of these antibodies that recognize some of this can mitigate some of the damage. So basically, the person that would have died instead just has a really crappy flu for a week, or maybe has some mild symptoms, depending on. It depends on the chemical signature and the body, and there's probably things we still don't understand about the interactions, but you're better off than you would have been. It makes the virus less severe. I was going to say something else, but it hasn't been proven, so I don't want to say that. So basically, it makes you somewhat immune to the virus. What we're seeing here, instead of this situation here where there's a black moon, we would see a yellow circle, or all three different chemical agents are different on the virus than is on the antibody, and the antibody doesn't recognize it. So it's a case of, Clark Kent and Superman, glasses on, nobody recognizes him in the comic books, whereas in real life, everybody would say, hey, that's Superman with glasses. You take the glasses off, you're Superman, you put them back on, you're Clark Kent. In real life, if somebody puts on glasses, we still know who the person is. If they dress up for Halloween, if their costume is just, a little bit different, we could still recognize them somewhat. We'll go up and say hi to them. But if they have a really good costume for Halloween, you're not going to know who they are, and they can get right by you, get into the cell, do what they want to do, replicate, and make the disease as severe as it can get. So that's what's happening, that's why they're calling it a novel, and I don't think the public really understands what novel coronavirus means. So that's what they mean. They mean it's part of the coronavirus family that follows the same set of rules for a specific type of virus. That's why it's in the family, but it's completely different. I guess you can relate it to, having, your own family, and you're used to your sister and, and your mother and father, and you're all sort of similar, and then you meet a third cousin that's completely different. I guess that's the best example. But in this case, that third cousin could kill you. So that's sort of what's happening with the science behind it. If you have any questions, leave them in the comments. I will try to answer them. I hope I simplified this enough. Like I said, this isn't the only process happening, but why we're having such an issue is that our bodies don't have any recognition of the novel coronavirus. Now, as more people get ill and recover, that's less people that can be infected in the population, and they should develop immunity to it. There was a case actually in Japan where people are talking about a reinfection, and I have not seen that in the literature that it's happening. Like I said, in science, it's a gray area. It's not being widely reported, so I wouldn't worry at this time. We have not seen reinfection that I know of, that I've been reading up on this. We have not seen reinfection of the same virus, because once you get sick, and you recognize you make antibodies that recognize it, it's going to stop the virus. Like I said, the difference comes in when the virus either mutates or if you have a completely new strain. And reports so far that I actually heard today, the virus is not highly mutagenic. It doesn't change its chemicals on its surface to trick your antibodies and get by them. So I fully expect, and what we've seen before, people gain immunity to the virus once they recover, and those are less people to spread the virus in the future. So this is also why they work on vaccines. Some vaccines don't work. They are testing vaccines out right now. They just reported one person got a trial vaccine. I hope it works. There's many vaccines out there that have been tried for different viruses, and it's trial and error. We don't know until we actually give the vaccine if it actually provides correlates of immunity, which I learned this semester. But it means it might not give us immunity. It might not give us these recognition chemicals that recognizes this virus. It's a difficult process, and each virus is different, bacteria different. It's our best guess. That's what science is. We're going off of best guesses from SARS, from MERS, and there was a drug that was developed, remdesivir. I'm probably butchering that. There's a drug developed against SARS and MERS that is showing in clinic that it also works on this new virus. They need to ramp it up. It might be a while before we see the levels that we really need for the medication. But there is past evidence that this family has behaved this way, and this virus is close to the other viruses. Unfortunately for our immune system, not close enough. This is exactly what's happening with bird flu as well. When you see bird flu, H1N1, it's these little spike proteins they're talking about. H1N1, H5N5, or H5N9. That's what it is. Your antibodies, your system does not recognize the virus because it's been circulating among birds. And it's chemically close enough to infect us, but chemically our immune systems don't recognize it, and that's what creates severe flu. And that's why we worry about the bird population, what's circulating in them if it transmits to humans. Sort of the same case in a way with coronavirus. It's just a brand new strain that we haven't seen, and immunologically we don't have the defenses to stop it. And in some people, it's mostly mild. In 80% of people, it's asymptomatic, meaning no symptoms or mild. But in the immunocompromised, in the older population, people with multiple, like diabetes and hypertension, their bodies are less healthy to fight off the infection. So this is why we're self-isolating. This is why we're trying to stop this virus. And said, if you have any questions, leave them in the comments, and I'll try to answer some more, and trying to think of more videos I can put out there that might help people better understand what's going on. Thanks.